Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at ARM with Ian Bratt, who's going to talk today about how to make sense out of all the different options you have between different processing elements that could potentially go into an inferencing architecture. So, Ian, how many different options are there to choose from for different processing elements?
Yeah, so machine learning is such an important workload that pretty much all processing elements have to be adapted and evolved for machine learning. And then, as opposed to which ones you actually choose, it really depends on your machine learning throughput requirements. So if you have huge requirements, you might need something built from the ground up, like an NPU. If you have more moderate requirements, then a CPU or a GPU might just be just fine.
Let's drill down into this.
Okay.
What are we looking at here?
Yeah, so like I mentioned before, what we're seeing in the industry is because machine learning is so important, we're seeing all pieces of IP, CPUs, GPUs, evolve for machine learning. That means like new instructions, new software to enable performance. We're also seeing new pieces of IP like NPUs, if you really need the best possible performance. Now, in terms of which one of these you actually choose, it really depends on your requirements. So, this is a simplified trivial graph, but you might have some sort of ML requirements plotted on the y-axis, and perhaps maybe anything this line below a CPU might just be completely fine. Now GPUs often in a lot of the systems where our IP is present, GPUs have a significant amount of compute horsepower, so they might be slightly higher than the CPU and perhaps cover a little bit more. And then if you really have the most possible the largest possible ML requirements, well, then maybe you're looking at an NPU, which would cover a much broader space.
When machine learning first started gaining prominence over the past few years, way beyond what it was before, everybody thought a CPU was sort of dead. But it's now, when you look at these architectures, there's lots of different elements in there, and the CPU does a lot of the prioritization, right?
Yeah, so I think that CPU architecture is definitely not dead. I think we're going to see a rich roadmap of improvements to CPUs for machine learning development. So both in terms of augmenting the CPUs to run machine learning workloads, as well as just the CPU continuing to play an important role of orchestrating the system as you have more and more complex systems with more discrete components.
I think most people are familiar that the GPU has done very well when it comes to a lot of the inferencing and also the training. The problem with the GPUs is that they're not terribly energy efficient, right?
Um, you know, I I'm not sure if there's anything inherently energy efficient about the GPU. It's just that they were built for one type of workload. Obviously, if you were going to start from the ground up for something like an NPU, you wouldn't. For machine learning workloads, you probably wouldn't have something like a GPU. It's really designed for a different workload, but it's got a lot of compute that can be reused for machine learning.
And the problem with an NPU is that it's very specific, right? So if the algorithms change, then potentially the NPU doesn't work as efficiently as some of the other ones.
Yeah, so there is this kind of balance between flexibility and programmability and fixed function, and the more towards the more you go towards fixed function, the better your performance and your efficiency. So that's why NPUs really have to kind of walk this tightrope of specializing for the stuff that is common, that's unlikely to change, but having some flexibility and programmability to kind of future-proof for new operators.
In a typical machine learning inferencing architecture, will you see all three of these in a chip?
I think it's really going to depend on the segment and the platform. So there are many markets today where you might just see a CPU and the CPU is doing the inferencing, and that works totally fine. There are other markets where you'll definitely see all three components and everywhere in between.
One of the problems with these architectures is that you want data throughput, you want massive speed in terms of processing power, but you also want to be able to utilize what you have there because otherwise it's almost like leaving inventory on the shelf. It's not very efficient.
Yeah, that's absolutely right. So that's where software is totally keen. So it's very important to invest heavily in software to really unlock the performance of any existing resources. If you're spending silicon for a CPU or a GPU, and you can use it for machine learning, then why not? You should be providing the enabling software to do that.
If you're building a machine learning architecture, what do you have to keep in mind? how are you going to make the choices between one and the other?
Yeah, again, that all comes back to your machine learning throughput requirements, and also what your existing platform looks like. So you might have an existing platform and it might have enough compute to handle your machine learning requirements. In that case, then you're just really missing kind of the software to unlock it. If your machine learning requirements are beyond what your platform currently provides, then you need to look at, you know, how do you ramp up that platform to meet those requirements? Do you add more CPUs? Do you add a GPU if you maybe need it for another system? Or do you add an NPU if you really need the best possible performance?
So let's look at a couple real world examples. So where would you need the most performance out of the NPU, for example?
There's a few different cases. So a very obvious one is for L4 self-driving cars. The machine learning requirements for self-driving automobiles are very, very huge, and you really want some sort of dedicated NPU for that sort of system, or multiple NPUs.
So where would you, if you take a look at a CPU and a GPU, where would those be most important?
So there are many scenarios where we see just a bit of machine learning creeping into existing workloads that are already running on a CPU. And so in those cases, what you're just missing is the software to run the machine learning on the existing CPU. So there are many cases like that where that's fine. Even simple things today like doing keyword spotting or detecting if there's a person in an image or not can be done running on a Cortex-M device.
Typically, when you design these architectures, are you going to see all three of those components in there, or is it going to be one or the other?
I think it's the answer is yes. These are just different tools in the toolkit, and based on the problem you're trying to solve, you'll see the appropriate collection. But it really depends on the problem you're trying to solve.
There have been some fairly significant changes coming out in terms of probabilistic type of AI versus Bayesian, for example. How does that affect any of these choices?
So if you look at the kind of further out technologies, like you mentioned Bayesian, some of these technologies they're pretty new. They're trying to find the right application, and for those sorts of areas, it doesn't get better than just classic CPUs. Classic CPUs are very good at lots of standard kind of high performance computing workloads. And so if you've got some new workloads coming up that are a bit more experimental, that may change, then you probably want to go with something that's very flexible like a CPU.
There are a lot of other moving pieces in here as well, too, right? So you have different memories and different memory architectures that could be coupled with the different processing elements. There's also the throughput, whatever your infrastructure is on the chip or off chip to move the data back and forth. How does that play into this?
Yeah, that really comes down to the role of the system designer. So the system designer has to have a good feel of the end use case that they're going to be running on their platform. And in those cases, you really need to work through the speeds and feeds for how data is moved around, where it is stored, how much storage is needed, if it's in on-chip, off-chip flash or off-chip DRAM or whatever. This really comes down to system design, bread and butter. Although it's not that different from just classic system design. It's the same types of problems, just data movement.
How about from a characterization standpoint? Is there any difference between each one of these?
In general, the CPUs, GPUs, NPUs, these are all coming from standard RTL, standard shippable ARM RTL.
So we've got multiple elements here. How do you glue the pieces together?
Well, one thing that's very important is, we need to provide the software to enable the ML performance across all three. But what's also important is basically providing an API that can actually abstract whether or not you're using a CPU or a GPU or NPU. The software guy's work or gal's work is hard enough as is. So if they just have a single API that they can target, and then underneath, if it's run on a CPU or a GPU or an NPU, they don't actually know, that's very valuable. So it's very important to have a higher level abstract APIs that abstract away a lot of the complexity underneath.
Ian Bratt, thanks for a great explanation.
Thank you.